Okay, so we will continue with the tutorial problems on molecular thermodynamics part. First we will talk about the problem of bond formation in a protein. So, the question is like this: a protein may contain several cysteines which may pair together to form disulfide bonds as shown in the figure below, means by the side. If there is an even number n of cysteine, n by 2 disulfide bond can form. How many different disulfide pairing arrangements are possible? So, the cysteine has S as a terminal group, and that S can form bond with another sulfur group, and therefore, cysteines can form disulfide bonds, and these bonds make a particular conformation of the protein more stable. So, here the question however, is much more theoretical in nature. So, if there are n cysteine groups, we know that there will be n by 2 bonds, because 2 cysteine group will form a bond, and how many such bonds or pairing are possible. Now, those pairings will be unique, indistinguishable pairing that you have to remember. So, if this picture may not be very clear. So, it is like this, that so here this is the third cysteine, this is the fourth cysteine, they are forming a bond, fifth and second are forming bond, and 6 and maybe 12 are forming bond. So, these are just examples. So, we can also think of the problem as a random chain of protein, where we have certain pair of I and j cysteine group that are forming bond, and then we pick among the rest of the n minus 2 more atoms and things like that. So, how we can think about that is that out of the n cysteine, we can take any 2 cysteine groups to form a bond in NC2 number of ways. That will leave us with n minus 2 cysteine residues. Again we can take 2 out of them to form a bond, that will leave us with n minus 4 cysteine. Again we can take 2, and like that we can continue, and then last 2 will form the bond in 2C2 ways, that means unique way. So, that will be the number of possible arrangements. Now, if I write it down, it will be n factorial by n minus 2 factorial and 2 factorial, followed by n minus 2 factorial by 2 factorial and n minus 4 factorial, followed by n minus 4 factorial by 2 factorial n minus 6 factorial, and it will continue. So, this n minus 2 factorial and n minus 2 will cancel, n minus 4 and n minus 4 will cancel, and what is going to happen, as you can see, that we will end up with n factorial by 2 factorial, 2 factorial, 2 factorial and things like that. So, how many terms will be there? As you can see that we are going to make n by 2 pairing. So, there will be n by 2 terms. So, therefore, n factorial by 2 factorial to the power n by 2, which is n factorial by 2 to the power n by 2. So, these many bonds will form, but these all bonds are unique ones right now. So, since we have no preference of any of those n by 2 pairings, the number of pairings possible will be n factorial by 2 to the power n by 2 n divided by n by 2 factorial, because n by 2 factorial we are doing, so that we are saying that all n by 2 pairings are indistinguishable, which means that 3, 4 and 2, 5 are not distinguishable, because they are just the pairings, they are just bonds. So, we are not distinguishing a bond between 3 and 4th amino acid versus 2nd and 5th amino acid versus 6th and 12th amino acid. So, these are the number of possible ways the pairing can be possible for n cysteines, where 2 cysteines form a double bond. Okay, the next problem: given a flat distribution from x minus a to x equal to x equal to minus a to x equal to plus a, with the probability distribution p x as 1 by 2 a, compute these quantities. So, these are practice problems for you, since you know that averaging is very important in statistical thermodynamics or molecular thermodynamics. Any observable you obtain is nothing but an average value multiplied or weighted by their own probabilities. So, here we are talking about a flat distribution, which means that the probability is same everywhere in the range of a range between minus a to plus a, it is same everywhere, and that value is nothing but 1 by 2 a. So, that will look something like that. And this kind of situation arises, as you know, for systems with all equal energy levels, where there is no preference between one energy level versus another one. And so, this is a situation something like that. Once you understand that, once you understand how to calculate the averages, we will be able to do that for other systems as well. So, let us calculate the average x. So, average x or any average value for that matter should be calculated either by sum or by integration. So, here we are going to use integrations, because here the x can take any values. So, the range of x is from minus a to plus a, and the average of x is nothing but x into p x dx. So, this is the formula. The reason is that any quantity that we are talking about, for which we are going to take the average, has to be weighted by the probabilities of obtaining that, and then dx is nothing but for integration sign. So, now it will give us minus a to a, and x is x dx, and we know the value of p x, which is 1 by 2 a, and that is a constant quantity. So, it is 1 by 2 a x square by 2 going from minus a to plus a, which is give us 1 by 2 a square by 2 minus a square by 2, which is 1 by 2 a square by 2 minus a square by 2, giving us 0. So, average value of x will give us 0. So, now I am going to do for x square average. So, x square average is not x average square, that will be wrong. So, it is minus a to a, nothing but x square, then p x and dx. So, you see I just replaced x by x square. So, imagine I am going to take an average of some quantity a, for which the probability is p x. So, it will be a p x dx. Now, a can be x or x square x cube, does not matter. Okay. So, we are going to do that. Now, this is again very simple, 1 by 2 a minus a to a x square dx, 1 by 2 a x cube by 3 minus a to a, which is a cube by 3 minus a cube by 3, 1 by 2 a cube by 3 minus a cube, which will give us plus. So, we are going to get 1 by 2 a multiplied by 2 a cube by 3, 2 cancels. So, we are going to get a square by 3. So, just to tell you that x average is called mean and x square average is the variance. So, here mean will be 0, because it is a flat distribution, it can be anywhere from minus a to plus a. So, mean is in the middle, whereas standard deviation will give you a measure of how much it goes, how much it varies, and it turns out that will be not the full a, but it is a square by 3, means if you take the root standard deviation of that will be the root of that. So, this is variance, and standard deviation will be root over of x square average, which is root over of a square by 3, which is 1 by root 3 into a. So, it is not fully the a, but it is little bit less than a when you calculate that average. Okay, so, now we have to calculate x cube average and x 4 average. So, without doing that averaging, for example, when you talk about x cube average, so it is again x cube p x dx. Now, you should know by now that when you are talking about an odd function are functions where f of minus x is minus of f x. In those cases, it will become 0. So, we can see that right now, and for the even functions where f of minus x equal to f of x, that will not be 0. So, we are going to do that again for x cube. So, it will be 1 by 2 a minus a to a x cube dx, which will give us 1 by 2 a x to the power 4 by 4 going from minus a to plus a, 1 by 2 a it will give us a to the power 4 by 4 minus a to the power 4 by 4 and going to give us 0. If we do x to the power 4, that will not be the case. If I just write the answer, I can write the answer now by following all the above ones is 1 by 2a to the power 5 by 5 minus a to the power 5 by 5, which is 1 by 2a to the power 5 by 5 plus a to the power 5 by 5, which is 1 by 2a to a to the power 5 by 5, going to give us a to the power 4 by 5. Okay. So, now we are going to go to the next problem. Okay. So, the next question is that what is the probability that in n coin toss there are small n heads and n capital N minus small n tails. If the coins are biased and has a probability p for head, if p can be anything other than half. If they are unbiased coin, then head and tail will have half probability, right. If they are biased coins, then it can have p can take any values. For example, if p is 1, there will be always head and never tail. So, what will be the probability? So, this question actually will lead us to understand what is called binomial distribution. We have already talked about it, but we are going to now discuss in light of this particular problem today. So, n coin tosses and small n heads, what is the probability, and small n heads and of course, rest of them tails, right. So, the probability is typically written as p capital N small n, which says that how many ways I can first let us calculate how many ways we can get small n heads out of capital N tail, and that will be n c n. That many ways we can do that first. I will explain that in a moment, and then we have small n heads with a probability p. So, it will be p to the power n. That means, the probability for tail is 1 minus p, and how many of them are there? Capital N minus small n. So, this is the probability of having n heads, small n heads out of capital N coin tosses, and this is called binomial distribution. So, this we know that for example, if we toss a coin, and you can ask a question that in n coin tosses, how many what is the probability that all of them will be head. So, that will be typically we say that it is half to the power n, half. However, here we are asking a slightly different questions, because we are asking that let us say 4 coin tosses, how let us say what is the probability of 2 being head and 2 being tail. So, that scenario can be understood from so many different possibilities. It can have this situation will satisfy the thing, this situation will also satisfy the thing, this situation will also satisfy. So, therefore, as you can see that out of 4 C 2, that means 6 possible ways we can have 2 heads and 2 tails, and since each of them are independent events, each of them will have probability half associated with it, provided it is a biased coin, then p and 1 minus p are equal, and therefore, p is half. However, if they are not biased, then we have to associate the probability as p to the power n, or here p to the power 2 and 1 minus p to the power 2 as well. So, and this is an important distributions, as you know, and the number of possibilities we have already discussed in case of Maxwell-Boltzmann distribution, that it is NCN. So, now we are going to see one application of that, which is in the next problem. So, suppose you synthesize a strand of DNA that is 1000 bases long. A process you use introduces a wrong base on an average every 1000 base synthesized, which means that if you synthesize 1000 base, there is a probability that one of the base may be wrong. So, the probability of wrong base is 1 by 1000, and probability that of correct basis of course is 999 by 1000. So, keeping that in mind, it is almost like this binomial distribution, right, because whenever there are two events, head or tail, or mutation or non mutation. So, there are two outcomes. So, then the probability will be either p and 1 minus p, and the distributions of that will follow a binomial distribution. So, here we can think that probability of correct basis is something like head, and probability of incorrect basis is something like tail. So, only thing is that the p is 999 by 1000, and 1 minus p of course is 0.001 by 0.001 or 1 by 1000. So, now the question is that calculate and draw a bar graph indicating the yield of each product DNA containing 0, 1, 2 and 3 mutations. So, it is asking us to plot the binomial distributions where small n in the earlier problem was 0 or 1 or 2 or 3. Okay. So, basically we are going to follow the same thing. So, here as you see that our head is equivalent to correct base with a probability p as 999 by 1000, which is 0.999. So, out of 1000 bases 999 are on an average correct. Our tail is correspond to mutated base or incorrect base. So, it is denoted as 1 minus p, which is 1 by 1000 or 0.001. Once we know that, we have to calculate the probability of p n n. So, where n equal to 1000 and small n equal to 0. How many ways you can do that? Of course, it is 100, 1000 C 0, p to the power n, which is 0.999 to the power 1000 of course, and 0.001 to the power 0. So, 1000 C 0 is 1000 factorial by 1000 factorial and 0 factorial, which is just 1, and 0.999 to the power 1000, this one of course will be 1, this is of course is 1, this one we have to calculate. So, let us use the calculator and calculate that. 0.999 to the power 1000, 0.999 to the power 1000, it is 0.368, 0.368 into 1, which is 0.368. Let us do the next one, p n equal to 1000 again, because out of 1000 bases we are going to consider n equal to 1, again that will be 1000 C 1, because the mutation can happen at any point, right. In the 1000 bases, the mutation can happen in the first base or in the second base or in the third base. So, there are 1000 possibilities for the mutations to happen, and that is what 1000 C 1 indicates. Now, 0.999 to the power. So, now this will be 999 and 0.001 to the power 1. So, this is nothing but 1000 multiplied by 0.999 to the power 999. Let us see how much it is. 0.368 again, and 0.001 is just 0.001. So, now if you multiply this one with this one, you are going to get 1. So, you are left with almost the same number. Now, let us see the next one, 1000 n equal to 2, that is going to give us 1000 C 2 multiplied by 0.999 to the power 998 into 0.001 to the power 2. What is 1000 C 2? So, let us do the complete calculation in the calculator. 1000 C 2, 999 to the power 98 and things like that. Okay, 1000 C 2 will do by hand, because calculator may not work. 1000 into 999 divided by 2, and then 0.999 to the power 998, which will be almost 0.368, and then 0.001 to the power 2. So, let us do that. So, as you can see, 1000 in this calculator, 1000 C 2 is giving error. So, we are going to do our own way. So, 1000 into 999 divided by 2. Okay. So, that is reasonable, and that is multiplied by 0.999 999 to the power 998 multiplied by 0.001 to the power 2. Okay. So, we will do step by step. Let us see how much this gives us. Okay. We will delete this one and see. Okay, as I said, that will be 0.368, and so, and how much we got that? 1000, or we can just write 500 because we know that, into 999. Okay. So, this much we got, and 0.001 to the power 2, 0.001 is 10 to the power minus 3. So, it will be 10 to the power minus 6, and if I do 10 to the power minus 6, it will become, let us say, I will do that 0.0000 1 2 3 4 0 1. So, it will be 0.184. So, I have just written down instead of doing it. So, 0.184, this is the value that we got, and now the last one, which is n equal to 1000, small n equal to 3, this will be 1000 C3 into 0.999 to the power 997 into 0.001 to the power 3. Now, first we will do 1000 C3, we will do one by one because otherwise it will not work. So, 1000 C3 is 1000 into 999 into 998 divided by 3 factorial, which is 6. So, that is this much. Okay. So, this is followed by 0.001 to the power 3. Okay, good, 0.166, and then we still left with, so this 2 gives 0.166, and then still left with 0.999 to the power 997. Let us see. It will be almost 0.368 though. Okay. We got 0.06 as the result, 0.06. Now, if you plot a bar diagram of those probabilities, P n n, which is 1000 small n, and this is small n, where small n is 0, 1, 2 and 3. So, bar diagram for 0 it was 0.368, and this is also 0.368. This was 0.18 and this was 0.067. So, the bar diagram will look something like this. So, as you can see that immediately when it goes to 3, the probability just dropped like anything. If you go to 4, it will be like 0. So, that means if the probability that 1 out of 1000 bases will be incorrect in a 1000 base sequence, then the fact that it will go to 4 or 5 is almost 0. It will not basically go to 0. So, it just shows that how the probability is going to change with the number of mutations given that the. So, it is like this, like if you toss a coin and know that head and tail are equally likely, then what is the probability that you are going to get like one after another tails or heads? What is the probability that you get 5 heads in a row? It will be very, very less. So, that is the thing. So, now going to the third question. Calculate how many combination DNA sequence of 1000 bases long contain exactly 2 mutant bases. So, it should be exactly 2 mutant bases, not more than that. So, since it has to get exactly 2 mutant bases, so what was the earlier question when you say n equal to 2? That time it was out of 1000 bases there are 2 mutations. Okay. So, how many possible ways you can get that? The question is that how many possible ways you can get that? Calculate how many combinations of DNA sequences are there. So, it is just asking not the probability, it is asking the combination. So, that is straightforward. So, it will be W is out of 1000 you are going to get 2 mutations, which is 1000 C2. So, it is 1000 factorial by 998 factorial and 2 factorial, which is 1000 into 999 divided by 2, 500 into 99, this many. Now, question number 3. What is the probability of having 500th base and 80th base mutated in the pool of DNA which has only 2 mutations? So, it is specifying the mutations exactly in the right place. So, which means that any 2 mutations, we have seen that the probability that there are any 2 mutations, which means when p is 1002, then it is approximately 1.18. But that time we considered mutations can be at any place. It can be at 1 2, it can be at 3 4, it can be at 3 and 27, it can be at like any 2 places. And how many such possible combinations are there? 1000 C2. Now, those 1000 C2 we have multiplied in order to get that. Now, we have to divide by those 1000 C2, because here the positions of the mutations are very specific. So, they cannot interchange. So, now we are going to divide by that 1000 C2, which is 0.18 into 1000. We have already done that, of course. It will be 499,500. Let us see how much that comes. Okay. So, it is 0.01234567, 3.6 into 10 to the power minus 7. That is the answer. So, now we are going to go to the last part of these questions. What is the probability of having 2 mutations side by side in the pool of DNA which has only 2 mutations? Now, earlier it was very specific 2 mutations. Before that, the positions of the mutations were not mentioned. Now, they are saying that they are together, which means the mutations can be at 1 and 2 positions, or 2 and 3 positions, or 3 and 4 positions. So, it can be any of those 999 positions, because it cannot be in the 1000 positions, because there are only 1000 sequence. So, it cannot be occupying 1000 and 1001 place, but it can occupy 999th place and 1000th place, first place and second place and things like that. So, the mutations are together. So, it is like this: mutations is let us say denoted by M, and right bases are denoted by R. So, it can be R R R, 998 of them, or it can be R and then MM, R R R, and rest of them. So, always they are together. So, that means there are 999 places that can be there. So, in the previous case we did not even specify any place, it was totally it was very specific, and before that it could have been anywhere else. So, we taking the answer from C, where no other possibilities were actually given, we can just multiply 999 with this answer, and then we can get that. So, this answer is of course only for this, because we are dividing by that. So, this is, I should write 1000 C2. Now, we take this result from the earlier result, which is 3.6 10 to the power minus 7, where it is a very specific mutations, and then there are 999 more possibilities are there in this case, and then that is what is going to give us. So, it is very approximately 1000. So, let us say it is very approximately 3.6 into 10 to the power minus 4. That will be the answer for this. Okay.